So, subject is EC3552 VLSI and chip design. In this unit 1 is about MOS transistor principles. So, in the previous videos we have discussed about MOS logic families, ideal and non-ideal IV characteristics. And in this video we are going to see about CMOS devices. So we know digital circuits are merely analog circuits used over a special portion of their range. When we use a special portion, then we can use it as a digital circuit, but it is actually analog circuits. So we are mainly going to see about the DC transfer characteristics of a circuit which relate the output voltage to the input voltage, assuming the input voltage changes slowly enough that capacitances have plenty of time to charge and discharge. So we are going to assume the input is going to change very slowly since it takes more time to charge and discharge. Next, here we are going to take only a specific ranges of analog circuits, that is the specific ranges of input and output voltages are defined as valid 0 and 1 logic levels. So, in this section we are going to see in detail about DC transfer characteristics of CMOS gates and POS transistors. So, this particular principles we are going to implement in the CMOS devices. So, in CMOS devices we are going to discuss about the DC transfer characteristics of CMOS gates and POS transistors. So, this is a table which clearly represents the relationship between the voltages for the three regions of the operation of a CMOS inverter. So, the three regions represents cutoff region, linear region and saturated region. And CMOS we know it has two transistors, one is NMOS transistors and PMOS transistors. This CMOS devices actually includes this NMOS devices and PMOS devices. So, how this actually works, this NMOS transistors, how it behaves in cutoff, linear and saturated, and this PMOS devices how it works in cutoff, linear and saturated, it is given here. So, this n suffix in the above this table we can split into two halves. The above half, the first half has a suffix n which represents it is a NMOS devices, that is VGS. GS represents gate to source, N represents for N transistor, NMOS transistor, and this GS actually gate to source voltage. P represents the PMOS transistor, it is a PMOS transistor. And in the first half we have all N suffix which represents it is an NMOS, and second half we have P suffix which represents PMOS transistor. And the basic condition we know in the cutoff region, actually the gate to source voltage is negative or 0. So that is it is less than threshold voltage in case of NMOS, but in case of PMOS the gate to source voltage is greater than threshold voltage. And for linear and saturated region, the gate to source voltage for linear it is little high than the threshold, but it is very high in case of saturated region. Actually it is opposite in case of PMOS transistor. So the gate to source voltage is less than threshold and it is more less than threshold in the saturated region, and accordingly how the input voltage here and everything it is clearly in this table. This table ensures the conditions for the particular transistors or the devices. Here in CMOS devices, our topic is CMOS devices. Actually we have two devices in CMOS devices, that is NMOS transistor and PMOS transistor. So according to the function we have to give the voltage operations which perform the transistor to be in the required region. So the above table we know it has various regions of operation for the NMOS and PMOS transistors. So also this table VTN represents the threshold voltage of the N channel device and VTP represents the threshold voltage of the P channel device. Also you note VTP is negative, that is the PMOS devices has the threshold voltage as negative. The equations are given in both in terms of VGS and VDS and V in versus V out. So that is equations are given for both gate to source voltage as well as drain to source voltage. As the source of NMOS transistor source, if for the NMOS transistor is grounded, then we have VGS is equal to Vin and VDS is equal to Vout. But in case of PMOS transistor, if we tie the source to VDD, then VGS is equal to Vin minus VDD and VDS is equal to Vout minus VDD. We have to subtract the VDD voltage from the input as well as from the output voltage. And this is the transfer function. So for the operation, so we have 4 figures here, figure A, B, C, D. So this top one represents A, this one B, this figure top one represents C and D. So here actually these 4 figure represents the CMOS devices operation. The DC transfer function, that is V out versus V in, for the static CMOS inverter is shown in the figure. So that is, here we have in the 4 figures, if you note, we have 2 colors. One is the gray color, another one is the light blue color. So this represents, this dark color represents for NMOS devices, the characteristic function of NMOS devices, and this light blue represents the behavior of a PMOS transistor. So it is mere opposite. So actually we know the DC function means output versus Vin. So here also if we see in figure B, we have the transfer characteristics for the dark gray color. Okay, dark blue color, it is represented for V out and the V in voltages. We have different input voltages, and what about the output voltages? So this dark blue represents the behavior of a NMOS transistor and light blue represents the behavior of a PMOS transistor. So let us discuss all these behaviors in detail. So our primary objective is to find the variation of the output voltage as a function of input voltage, because it represents our DC characteristics. So because this DC characteristics represents the CMOS devices operation. So this we can done. How we can find the output voltage means, this is very easy if we do with graphical analysis. First we can have various sources of Vin, various values. We can change various input voltages. So for a given V in, we must find the V out subject to the constraint that for IDS for NMOS is equal to IDS PMOS. So you see the above graph once again. IDS is equal to this one, first graph, A graph. If you look at, you can have both IDS, the dark blue represents NMOS and this P suffix represents PMOS devices. It is positive for IDS, the value of current, that is drain to source current in NMOS devices is equal to the drain to source current in the PMOS. It is in the first quadrant, but here it is in the below quadrant. For simplicity, we can assume that the threshold voltage for PMOS and threshold voltage for NMOS should be equal, but it is inverter. Okay, if it is positive plus, next one will be the minus 5. That the PMOS transistor is 2 to 3 times as wide as the NMOS transistor. So we have N is equal to P. The plot also shows IDSN is and IDSP in terms of, that is drain to source in NMOS and drain to source current in PMOS in terms of VDSN and VDSP for various values of VGSN and VGSP. That is which graph? So VDSN and VDSP. So okay, A graph. Okay, so this A figure represents the plot for current and the voltage. VI characteristics for NMOS and VI characteristics for PMOS devices we can discuss. Next we will go to the figure B. So the figure B shows the same plot between IDSN and IDSP now in terms of V out for various values of V in. That is drain to source current for various output voltages. Figure B, you see here. Here we are going to see about the IDSN, that is the drain to source current and drain to source current for NMOS and PMOS, and for various input voltages. We have V in 1, V in 2, V in 3, that is various input voltages. And what about the output values for each we are going to get from figure B. Okay, the possible operating points of the inverter are marked with dots or the values of V out, where VDSN equal to VDSP for a given V in. So that is the operating points. So okay, here it is represented in dots. Okay, the operating points are represented here. It is marked in dots. You see in the graph B, if you look at here, we have two dots which represents the operating points. These operating points are plotted on V out versus V in axis. Are also clearly shown in figure C in order to show the inverter DC transfer characteristics. Okay, this figure C represents various operating points. Here you see A, B, C, D, E. 5 points we have plotted. So that is in the V out. Okay, VDD plot we have 5 operating points. That is in figure C we have operating points plotted in the V out versus V in. Next, in figure D, if you see the supply current IDD is equal to drain current should be equal to drain to source current both in NMOS and PMOS, and it is also plotted against V in figure D. So ID versus V in, D fourth current, IDD drain current versus input voltage. What about the input voltage and the final drain current? Here we are assuming both the drain current in case of NMOS and PMOS should be the same. So that is the fourth plot. That is, the figure D shows that both the transistors are momentarily on as V in passes through the voltages between ground and VDD, resulting in a pulse of current drawn from the power supply. The operation, the figure C, once again come back to the figure C, we have 5 regions, okay, marked as A, B, C, D, E. For example, if you see in region A, the NMOS transistor is off, so the PMOS transistor pulls the output to VDD. First we will see the region A. Region A, NMOS is off. So here, okay, in this plot C, the point is A. If you look at the point A, NMOS is off and PMOS transistor is on. So it is at the value VDD, that is A region. Next, in region B, the NMOS transistor starts to turn on, pulling the output to down. So it is getting down. So okay, initially the NMOS is off, but here at region B, NMOS is going to turn on. So it tries to bring the VDD to a lower value at point B. In figure C, if you look out at point B, the VDD starts to get down. Next, in region C, both the transistors are in saturation. So it is at C region. If you look at the figure C, at region C, both the transistors are in saturation. Next, notice that the ideal transistors are only in region C for V in equal to VDD by 2, and that the slope of the transfer curve in this example is negative in this region, corresponding to infinite gain. Also, we know the real transistors, that is the ideal transistor will be stay in the region C. In the graph C, if you see, it is the region, ideal region. Real transistors have finite output resistance on account of channel length modulation and thus have finite slopes over a broader region C. But really, ideal is one condition, but really we have a slope. It won't be like this, the region C. Look at the figure C. Figure C, the region C, it is to be ideal case, but it won't be like this. We have a slope in a real transistors. Okay, it won't be like as in the figure. For real transistors, we have some slope. In region D, the PMOS transistors is partially on, and in region E, it is completely off, leaving the NMOS transistors to pull the output down to the ground. So last region, okay, D and, okay, if you look at the figure D, this region, figure C, At point D, now NMOS is slightly going to turn on. Okay, that is here NMOS is slightly going to turn on, and at the point E, NMOS is totally on. So it brings the output VDD to the 0 value. So that is 5 regions we had discussed. So also if you notice, the inverter's current consumption is ideally 0. Ideal condition is 0. There is no current consumption, neglecting the leakage current when the input is within a threshold voltage of the VDD, or either it is VDD or ground rails. This feature is important for the low power operation. So finally we can conclude the 5 regions in the figure C. Okay, here in figure this figure. In this figure C, we can conclude, summarize. In figure C, we have 5 regions A, B, C, D, E. So these 5 regions we can summarize here. So region A means it is input voltage is between 0 and threshold. So N device is cut off and P device is linear. So we get output equal to VDD. And similarly, region B, the input voltage is between threshold and VDD by 2. So here P device will be in linear and N device in saturated. So we get V output equal to VDD by 2. In C region, we have input voltage is equal to VDD by 2. So P device, both the devices are in saturated. So V out sharply drop down. Now it drops from VDD, higher value, to the lower value. At region D, the input voltage is between VDD by 2 and VDD minus threshold. So here P device will be still in saturated, but this N device slowly enter into the linear device. So it brings the output still to a lower value. And in region E, the input voltage is still lesser than the VDD minus threshold voltage. So automatically now the P device also enters into the cutoff region. From the saturated, it enters into a cutoff region, and N device it maintains in the linear region. So it brings the output to a low value, 0 value. So also in these devices, these CMOS devices, it also exhibits beta ratio effects. It's a wonderful effects we can discuss. So from this figure, it shows the simulation results of an inverter process. The PMOS transistor is twice as wide as the NMOS transistors, we know. So from the design, it is twice as wide as the NMOS transistors to achieve approximately equal betas. So we know simulation matches the simple models reasonably well, but the transition is not quite as steep because transistors are not ideal current sources in saturation. In the ideal, it won't be a ideal current sources. The crossover point, where the crossover point, V invert equal to V in equal to V out. This we can call as a crossover point. This is called the input threshold. We know because both mobility and the magnitude of the threshold voltage decrease with the temperature for NMOS and PMOS transistor, the input threshold of the gate is only weakly sensitive to temperature. We have seen that for P equal to N, the inverter threshold voltage is V in is VDD by 2. That we clearly see. But this is desirable because it maximizes noise margins and allows a capacitive load to charge and discharge in equal times by providing the equal current source and sink capabilities. So this beta effects, it is very important. Inverters with different beta ratios, that is R equal to P by N, we are called this point as skewed inverters. If R is greater than 1, the inverter is high skewed. If R is less than 1, the inverter is LO, low skewed. If R is equal to 1, the inverter has normal skew, or we can call it as unskewed. A high skew inverter has a stronger PMOS transistor. Therefore, if the input is VDD by 2, then the expected output is greater than VDD by 2. In other words, we can say the input threshold must be higher than for an unskewed inverter. Similarly, for a low skew inverter has a weaker PMOS transistor and thus a lower switching threshold. So again from the same figure we can also see the impact of skewing the beta ratio on the DC transfer characteristics. Beta with respect to the DC, that is output versus input voltage. As the beta ratio change, the switching threshold also moves. Where the curve it moves towards right. So that is the switching threshold also moves. However, the output voltage transition, that is, it remains sharp. We know gates are usually skewed by adjusting the widths of the transistor while maintaining the minimum length for speed. However, velocity saturated inverters are more sensitive to skewing because their DC transfer characteristics are not as sharp. DC transfer characteristics of other static CMOS gates can be understood by collapsing the gates into an equivalent inverter. Series transistors can be viewed as a single transistor having greater length. If one of the several parallel transistors is on, then the other transistors can be ignored. If several parallel transistors are on, the collection can be viewed as a single transistor of greater width. So far we have discussed about beta effects, and also CMOS devices means it has a good noise margin. So we'll discuss about a noise margin also little bit in this topic. Noise margin is closely related to the DC voltage characteristics. So this parameter gives you allowable noise voltage on the input of a gate so that the output will not be corrupted. The specification most commonly used to describe noise margin, it uses two parameters. One is low noise margin NML and another one is high noise margin NMH. So from the figure we can clearly understand. Okay. So logical high output range. So this inverter represents output characteristics. This side represents, right side represents the input characteristics. So okay, and this one is the high output range. So left side is the output and right side is the input. So above one is the high output. So OH means the suffix OH represents high output. OL represents output low. Similarly, NMH means noise margin high. Okay, IH means input high, input low. So now I hope that the parameters will be clear. With reference to the figure, NML, that is defined as the difference in maximum low input voltage recognized by receiving gate and maximum low output voltage produced by the driving gate. That is NML equal to VIL minus VOL. Okay. Similarly, the value of NMH is difference between the minimum high output voltage of the driving gate and minimum high input voltage recognized by the receiving gate. Thus, NMH equal to VOH minus VIH, where VIH represents minimum high input voltage and VIL represents maximum low input voltage, and VOH represents minimum high output voltage and VOL represents maximum low output voltage. We know inputs between VIL and VIH are said to be in the intermediate region. So okay, here if you see this VIL and from the figure, if you see the difference between the region between VIH and VIL represents the intermediate region or forbidden zone and do not represent the legal logic levels. Therefore, it is generally desirable to have VIH as close as possible to VIL and for this value to be midway in the logic swing, that is VOL to VOH. This implies that the transfer characteristics should switch abruptly. That is, there should be high gain in the transition region. For the purpose of calculating noise margins, the transfer characteristics of the inverter and the definition of voltage levels VIL, VOH, VOL, VIH are shown in the figure. Logic levels are defined at the unity gain point where the slope is 1. So that is, it is shown in the figure, that is unity gain points where we have the slope to be the 1. If either NML or NMH for a gate are too small, the gate may be disturbed by noise that occurs on the inputs. An unskewed gate has equal noise margins which maximizes immunity to arbitrary noise sources. If a gate sees more noise in the high or low input state, the gate can be skewed. If we have more noise means then we can skew to improve the noise margin at the expense of the other. So we also study about the beta ratio. There we discussed about skewing. So if the noise margin, if the noise is high, then we can skew. Okay. Note that if VTP is equal to VTN, then the noise margin high NML and NMH increase as threshold voltage also increases. So, okay, the relationship between the noise margin and the threshold voltage is directly proportional. Quite often noise margins are compromised to improve the speed. Noise sources tend to scale with the supply voltage, so noise margins are best given as a fraction of the supply voltage. A noise margin of 0.4 volt is quite comfortable in a 1.8 volt process, but it is marginal in a 5 volt process. So we have discussed about the noise margin, beta effects. So all are important under CMOS devices. So all these topics I referred from the book Neil H.E. West, so which is the first textbook given in your syllabus also. Thank you.